next problem. The velocity and acceleration of a particle at t equal to 0 are u equals to 2 I cap plus 3 j cap meter per second, and k is equal to 4I plus 2j meter per second square. Calculate velocity and the displacement at t equal to 2 seconds. This is the question. Right, we can see that the acceleration is a constant value here. There is no t present in A, right? In the equation of t, if you have a term, any term related to time, then that is not a constant. So since acceleration is a constant, right, I can apply the those equations corresponding to constant acceleration. When acceleration is constant, we can write the velocity v is equal to u plus a into t, right? So this is applicable even if the notation is in the vector format or a complex IJK format, any form. So using the vector notation, this is 2 I cap plus 3 j cap. This is u plus acceleration, that is 4 I cap plus 2 j cap into time, that is equal to 2, right? So at the end of 2 seconds, we have the velocity that is equal to okay, this is 10 I cap 3 plus 4, so plus 7 j cap meters per second is the answer. And we want to calculate the displacement, so use this equation. S is equal to ut plus half at square. U is equal to 2I plus 3j cap into 2 plus half into acceleration is 4 I cap plus 2 j cap into t square, so 4. All right, so this means the displacement is equal to 4 plus 28, so this is 12 I cap plus 6 plus 4, so this is 10 j cap meters. Okay, straightforward answer. Okay, let's move to the next question. The velocity of a particle v is equal to 2t into I cap plus 3t square into j cap meters per second. Okay, if Okay, if the particle starts from 2 comma 4 at t equals to 0, then find the following. So part A of the question, the acceleration at t equal to 1 second, then B, the coordinates at t equal to 2 seconds. Okay, so the velocity has been given, and the first part of the question is to find its acceleration. Okay, so to find acceleration, we know that acceleration, this is answer to part A question. So acceleration A is equal to dv by dt. So since v is a function of time, right, you can see here, the v is a function of time. There is t and t square given, which means it is a function of time. So I can apply the derivative, and I can get the derivative by taking the differentiation of this v. So dv by dt, that means I'm supposed to perform the d by dt of that term, that is 2t into I cap plus 3t square to j cap. So I and j cannot be integrated or differentiated. They will remain as it is, but the remaining terms you can differentiate or integrate. So differentiation of 2t is 2, okay, 2 into I cap, and the 3t square can be differentiated to get 6t, okay, into j cap. So this is the acceleration in meter per second square, but the question is at t equal to 1. So at time t equal to 1, what happens to acceleration? This is 2 into I cap plus 6 into 1 is 6 j cap meter per second square is the required answer. This is the answer for part A of the question. All right, very similar to this. Now we have to solve the second part of the question. That is, we need to find the coordinates. In the sense, this is related to the position, okay, or the displacement. So part B of the answer. So in order to find where is it located, right, or actually in order to get the what you call coordinates, I have to perform first I need to find the position vector. Position vector will give you the x comma y coordinate. So I need to find that. So in order to get that, I need to find the what you call S, right? S is equal to, so S is equal to integration V into dt, right? S is the position, right? If I'm writing V in the vector format, I'm going to get S in the position vector format. Okay, so I'm supposed to do in this way. This is equal to, I'm supposed to integrate the 2t into I cap plus 3t square into j cap with respect to time. All right. So I'm supposed to perform the calculation with respect to time. So that is dt. All right. So this is going to give you the initial to final value of my r, right? So S is nothing but the total difference. So I'm supposed to write R, that is the position at 2 second minus the position at say the 0 second, right? 0 second is nothing but integration will happen from initial position to last position of time. So time starts from 0, time goes till 2 because the question says find till 2 seconds. All right. So under this condition, So I'm supposed to do this integration itself. This is 2t I cap plus 3t square j cap into dt. So r, that is a position vector at 2 second minus the minus the position vector at 0 second is equal to, let's do the integration first, then we'll see what we can do. So the 2t when integrated becomes t square into I cap plus the 3t square what I have becomes t cube, okay, into j cap. This is my function and I'm going to put the values 0 and 2 here because that's what is the meaning of the integration from 0 to 2. So this means r at 2 second minus r at 0 second is equal to, put 2 there, so 2 square is 4 I cap plus 2 cube, that is 8 j cap, minus 0 into I, so that is a 0. 0 into j is a 0, so it's just only this part, 4 I cap plus 8 j cap. So the r at 2 second is equal to, I can rewrite this as, say this is equal to 4 I cap plus 8 j cap, this term, plus I have to perform the r at 0 second. What is r at 0 second? It's the initial position, right? So you can see that initial position is given as 2 comma 4. So I can write in the vector format as 4 I cap plus 8 j cap as it is, plus, so r at 0 second is the initial position 2 comma 4, right? So 2 comma 4 means that is 2 into 2 along x axis plus 4 along y axis. So the position vector of this particle after 2 second, that is r 2 second, is equal to 4 plus 2, that is 6 I cap, 8 plus 4, that is 12 j cap. This is the position vector. So position vector indicates that points out to a point 6 comma 12. So what are the coordinates? So they have asked this question, find the coordinates. So coordinates at t equal to 2 seconds are, I can simply see the position vector, it is 6 comma 12. Okay, so this is the required answer. Okay, moving further. All right, now we'll move on to the next set of problem that includes graphs. So I need to identify various types of graphs that could give increased velocity, decreased velocity, constant velocity, and constant acceleration, increasing acceleration, decreasing acceleration. Everything we can identify by just looking at graphs. So the graphs are the mostly important type of analysis of motion. Okay, so let's look at some of the points that directly are derived from the motion. Right. So what are the possible graphs that we can plot? The normal graphs that we plot, one is S dash T. S dash T is S is displacement versus time. Okay, another V dash T, that is velocity versus time. Okay, another one is acceleration versus time. And also we can plot the velocity versus displacement. These are the most common graphs. So whenever we want to analyze the motion, we use one of these 4 graphs, right? Depending upon various types of S and T graphs, we can identify various types of motion. Similarly, V versus T can also be used to analyze what type of motion it is, and so on, right? We can do a lot of calculations based on this. Okay, now when I say S, T, V, T, etc., you can see that this actually corresponds to one of them is being used as a x-axis and one of them will be the y-axis. So, right? So this could be, there is a x parameter, there will be a y parameter. So normally if I say ST, so this will be S is along y-axis, time is along the horizontal axis. As the time changes, what happens? Right? So like that, I can try to understand what happens. Right? So if this is, again, this is time, say this is displacement, and if I get a straight line, it means, okay. At the same time, if you get, if I say that I get a equation, I get a curve like this, means something. The motion may be uh, with decreasing velocity, possible, right? I have to analyze this. So right now I told at random, right? If you get a curve like this, it means something, right? Motion is a certain kind, right? So we need to identify that by looking at what type of graphs we have. Okay, now so the shape of the graph, right, will be decided by the equation that decides x and y. So how do you relate y with x? Y with x indicates s with the time, or v with the time, or a with the time, or v with s. Any of the them. How do you relate, right? How they are related to each other, that will decide the shape of the graph. So the shape of graph is decided by the relation between x and y of the curve, of that particular curve. It can be anything. Okay. Then if at all I put x equal to 0, and if I get y is also 0, then by default the graph passes through origin. Right? So this is also important. This is what we do in normal analytical geometry, right? So if the x means x coordinate, if x equal to 0 implies y is also 0, this means graph passes through the origin, right? Otherwise, it is not going to pass through origin, right? Now, let us try to define a new parameter. So that is, let the z be equal to dy by dx. That's a differentiation, right? The value of z at any point can be obtained by the slope of the graph. So this z means the differentiation gives you slope. Okay, so slope of the graph, right? This means, for example, if I'm having the graph as st graph, displacement versus this is example. If I'm considering st graph, what is ds by dt? So the ds by dt is nothing but velocity. You see, you can find the velocity. Slope is nothing but velocity of graph, right? Slope of ds, the st graph gives you velocity. So this is the point which I wanted to make. So slope of st graph, right, gives velocity. One point. Okay, we can make many such points, but as of now, this is just an introduction. So let's not look at more detail. Right. Then also I have another point to make. Let me denote the dz is equal to integration y times dx. So this actually implies the I can write it as z, or the z final minus z initial is simply the or it is delta z. This is equal to, integration gives you the area. Okay, so integration of any curve is the area of the y-x graph. So once again, I'm going to give an example here. So this is the example where we apply such thing. So if you have, let's say s is equal to integration v dt. So this means I'm trying to calculate, if I try to find the area of vt graph, right? So that is area of vt graph gives the value of s, right? What is s? S is the displacement. So it's not necessary to use equations always. Even if you have the graphical representation of the motion, still you can get the various parameters from that particular graph. All right, so let us try to analyze this particular thing using a small table. This is going to give you the complete idea what I told you so far. Okay, so this is on the left hand side, I'm going to write what graph I'm considering. And if at all I try to find the slope of that graph, what I'm going to get. And if at all I try to find the area of that graph, what I'm going to get. Okay, this is what I'm trying to write. So this is my table. So let's assume that we are going to use first graph as ST graph. So when I use ST graph, the slope is ds by dt, which is nothing but the velocity, right? And when you integrate the s, you are not going to get any physical quantity. So this is not a physical quantity. You don't get any physical quantity if you integrate that particular graph. Okay, so just remember, there is no meaning in integrating a ST graph. Okay, let's move further. Let's move further, and now the second graph we are going to consider is a VT graph, velocity versus time. So dv by dt is acceleration, and when you integrate right v dt, you are going to get the displacement s. So if you have a vt graph, you can find displacement or the acceleration. So okay, then let's move on to the next graph that we are going to consider. That will be a AT graph, AT. So differentiation is dA by dt. The dA by dt has no specific physical quantity, but definitely you can get the rate of change of the acceleration. If needed, you can use this. Okay, but when you integrate, you are going to get the velocity. So integration of a dt is going to give you what is called as the velocity. So this is a very important table that can be used at various points. Okay, now So this is a general idea, right? Generally, these points are valid for any type of problem. Okay, but moving further, now our intention is to apply and seize the specific type of problems. The first type of motion is the uniform motion, and let us consider what are the types of graphs we are going to get for uniform motion. So when I say uniform motion, the basic condition for uniform motion is acceleration is equal to 0, right? And velocity is a constant, right? Which means what is s? Distance is equal to velocity into time. And also you can calculate s is equal to some initial displacement plus velocity into time. So these are the four basic equations governing the uniform motion in general. So these are the four equations I need to remember when I say uniform motion. So corresponding to this, let us try to write the corresponding graph, right? If I try to write a ST curve, right? What is a S versus T curve? You can see the S versus T curve here. So as an I see, S versus T curve is this and this. They are straight lines. In the sense, if I plot a S versus T graph, it will be it's going to be a constant. It's going to be a linear curve, straight lines. This is my first observation. And as I say, acceleration is 0, right? That's the first case. Otherwise, even the acceleration, you can say that it is a constant. So the general curves of uniform motion are as follows. Again, we are trying to write them in the following fashion. The first one is acceleration is equal to 0. Let's write that curve. So acceleration is equal to 0. That has to be. So this is the first curve for that. So I'm simply plotting acceleration. So horizontal axis is time and this is acceleration. A is equal to 0. So let us plot A equal to 0. So this is 0 throughout, right? So A value is equal to 0. There is no amplitude for this, right? So red is my graph. It is along x-axis itself. So this is A equal to 0 curve, right? This is the first condition for uniform motion. Then let's go for the second condition. And the second condition says that velocity is a constant. So I'll plot a velocity curve. Okay, and this velocity has to be a constant. So it has constant means irrespective of the time, velocity will not change, right? This is time. So this is the velocity is a constant value. Constant value will be given by some value. Maybe if this is 3, so velocity is 3 always. Velocity is not changing. Okay, that's the second curve. And the third curve is S is equal to Vt, right? As distance is equal to velocity into time. So let us try to plot that graph like this. So I'm trying to plot either S versus time. So if it is Vt, it looks like y is equal to m into x. So m into x is a straight line. So that curve, again, you can see that it passes through origin. So my curve is this. Okay, this is the curve S equal to Vt. Otherwise, if at all there is a initial displacement, then my equation or then my curve will look like this. Okay, in that condition, under that condition, I can write this is the time and see this is the displacement. If at all there is a initial displacement, then the curve should be starting from some S naught plus something. Okay, so this will be the initial value of S, that is S naught. So this equation is nothing but S equal to S naught plus velocity into time. That's the equation. So if at all you see either of these four, right, plots, then you should conclude that, okay, the motion that has been represented by the curves is a uniform motion. Right. Remember these four equations and you can relate those four equations into the curves when and as and when required, so that you can identify whether the curve is like this. Okay, whether the motion is uniform or not. We can simply identify like this. Okay, let's go to a quick problem based on this. Okay, so this is S versus T, and the curve given here is like this. Okay, so this value is 10. This is equal to 5. Right. So the question is find the velocity. This is the question. Okay, now you see this is a S versus T graph, and from the basics we know that if the S versus T, the displacement versus time graph, is a straight line, right, then this means it is a uniform motion. Correct? So my first conclusion that I should derive here has to be the same thing. Okay, so this is the ST graph, right? And I can see that this is a straight line. This implies it is a uniform motion. Right, let me go back to the table. And the question says, find the velocity, right? How do you find the velocity? Right, ST is given. This is a graph. If you want to find V, you need to find the slope. That's all. So find the slope of that particular curve, right, shown in ST to get the velocity. Okay, now how to find the slope of this curve? Slope is nothing but change in y with respect to change in x, right? So that means, okay, let's write in this way. So velocity is nothing but, if it is a variable curve, then it has to be ds by dt, right? You can write like ds by dt, provided it is a function of time. But as of now, I cannot relate it. So I have to write it in this way. This is change in s divided by change in time. So you can, if you can find how much it changes, right, in a given time, I can calculate that. You see here, let me mark the change in y. So the change in y axis is this much. You see, the y value changes from 10 to 0, right? The y value changes from 10 to 0. Within the same duration, the x value changes from 0 to 5. Okay, so the final value minus initial value is the change, right? I can write it in this particular fashion. So that's what I want to write. So change in s value I want to see. So the final value, initially it is 10, and at 5 it becomes 0. So you see, the final value is 0, initial value is 10. So final value, that is 0 minus initial value 10 divided by, look at this, the change in time, right? Change in time, initially 0, finally 5. So final value 5 minus initial value 0. So this is basically minus 10 by 5, that is equal to minus 2 meters per second. Okay, so that's how we calculate the velocity. All right. Another question. So this is S versus T, and the values are, this is minus 20 and this is 10. All right. So once again, the question is to find the velocity. Okay, this is find velocity. Yes, the velocity is 2 meter per second. Right, so how to calculate? So velocity V is equal to, I want to write ds by dt, which is nothing but delta s by delta t. So we can see that change in s is nothing but final value minus initial value. Final value becomes 0, initial value is minus of minus 20, so that is plus 20 divided by time. Final value is 10, initial value 0, right? So this is 20 by 10, so 2 meters per second. Okay, then fine. Let's move on to the next topic, right? Next kind of motion that we are going to consider is uniformly accelerated motion. So previous one was uniform motion where acceleration was 0, right? The next one is uniformly accelerated motion. Right. So let us simply try to write an equation, write the set of equations. Okay. So here uniformly accelerated acceleration. So A, this is going to be a constant curve. So because of this, we can write V is equal to C, initial value plus AT, right? This is one equation. I can see that this is a straight line. Y is equal to mx plus C. Or if at all initial velocity is 0, then v is equal to at, that is also a straight line. Okay, so this is if u is equal to 0. My second sets of equation. And let's try to write an equation like, okay, displacement. So displacement S is equal to, you see, ut plus half at square, or this could be S is equal to simply half at square. Once again, if the u is equal to 0. Right. And I know that I have another set of equation describing S, provided you have some initial value, that is S naught. S naught plus the same thing, ut plus half at square. This could be the case, or if u is 0, I can write S is equal to simply S naught plus half at square, right? This is when u 0 and S is not 0, right? For the second case. right? So this is when u is equal to 0. So these are the equations which we can consider. Okay, now I have to see how these graphs are going to look like whenever I try to plot. So, but before that, let me make an important note that these are the equations to be considered for uniformly accelerated motion. So, A becomes a constant. So, whenever A is a constant, let me write the required graph. This is the time versus acceleration. So it is a constant. So as soon as I say a constant, this has to be a constant value irrespective of the, sorry, this is a constant value irrespective of, just a second. So it is a constant value irrespective of the time. So that is a curve for uniformly accelerated motion whenever I try to plot a AT graph. Okay, so the second equation is going, the second set of equations, that is this and this, are going to be the straight lines whenever you plot VT graph. So VT graph of the velocity versus time graph of a uniformly accelerated motion should be straight line. Okay, right? So let's try to plot them now. This is the first one. I'll also plot the next VT graph. Another VT graph like this. So we know that this is velocity versus time. The velocity versus time. So the first one, v is equal to u plus at, indicates that there is a initial velocity u from where the graph begins. So that is from u it begins and it goes on like that. At the same time, if you have u0, this has to start from no initial velocity, so this has to be like this. Okay, so this is the v is equal to u plus at. This is v equals to just at, thinking that u is equal to 0. Okay, moving further, we are trying to write the S graph now, right? For S, you can have ut plus half at square, right? When the time is equal to 0, this is also going to start from 0 itself. Okay, but even if u is 0, it's half at square, but still it starts from 0. So this both curves will start from 0. Whereas, if you look at the next curve, these two curves will not start from 0, they will start from some s naught. Okay, so whether u is 0 or not, it doesn't matter. The curve either will start from 0 or not, provided there is a s naught or not in the given equation. So let's try to look at that now. So I'm trying to plot the curves for the last two lines of the page. Okay, let me write the two graphs over here. Let's plot. This is one plot for me, and the second plot will plot over here. Okay, so my intention is to plot S versus T. So S, this is S versus T, S versus T. Now, if at all, right, I'm trying to write this. S is equal to ut plus half at square, or S equal to simply half at square. Put t equal to 0. S also becomes equal to 0 in both the cases. So And it is not a linear equation, it is a parabola because of the term half at square. So it begins from 0 and it goes, right, uh, in a different fashion, right? So let's write this way. So the curve will look like this. It's not a straight line, right? So, right, this is the curve, either S equal to uh, the ut plus half at square, or the S is equal to simply half at square. Then how to differentiate whether there is u or not? That can be identified by initial slope. So this is the initial slope, gives you an idea that is equal to the initial velocity. Okay, our initial velocity, anyway, we know that it is denoted as it is u, so I will simply write u here just to denote this. Okay, initial slope equal to u, I'll write initial slope equal to u value. How do you find initial slope? Differentiate ds by dt and put t equal to 0 over there. If it gives you a value, then that is the initial slope or initial velocity. Okay. At the same time, let's go to the second case. There is a S naught. So the curve begins from the initial, from a position, and that position is called as S naught. So start from an S naught, then goes in this way. So this curve will be S equal to S naught plus ut plus half at square. Right? So this is the value denoted by S naught, initial value. Okay, right. So in this particular scenario of uniformly accelerated motion, see, the A is considered as a constant, and I have to mention that A is positive. In the sense, acceleration is a constant and a positive value. The velocity keeps on increasing. As the time progresses, the velocity keeps on increasing. Okay, at the same time, there is another type of uniformly accelerated motion with acceleration being a negative. Okay, if that is a condition, once again, we are still in the same uniformly accelerated motion, but this acceleration is negative. So we call that as the uniformly, either you can call decelerated motion or you can call retarded motion. Okay, so this motion is normally considered until, only until, because velocity keeps on reducing, right? So you can consider this motion until v becomes equal to 0, right? So as and when v is not 0, you can apply negative acceleration to bring it there, bring it down to 0, right? So the same concept, when a vehicle is in motion, you can apply brakes to perform the deceleration and bring it down to 0. But after 0, there is no question of further decelerating. So there is no negative v value coming into picture. So under this condition, what are the equation? So the acceleration, the a is a constant, but this is negative. First point. So because of a being negative, the velocity will be initial velocity minus at, straight line but in a different way. And we can write the s, distance covered, is also equal to ut minus half at square. Okay, so using this, we can try to find out the various graphs associated with the uniformly retarded motion. So again, these are the important equations. Now let's quickly write the required graphs for this. Okay. So the first graph, A is a constant and it is negative. So whenever I want to plot a negative value comes below the x-axis, right? So if I consider x-axis like this, then you see the acceleration comes below this. So this is, say, time versus acceleration, and acceleration is negative. Negative acceleration is always indicated below the x-axis. So this is constant and negative value for A. Okay, A is negative, so this is 0. So below 0 means it is negative value. That's the first graph. A is negative, and initially you have a velocity u, right? But the final velocity is always 0, right? So you can see that the equation will look like this. That is, the v is equal to u minus at is a curve like this. So my intention is to plot this. So this is the actually I'm trying to plot velocity versus time. So velocity initially begins at a point and then keeps on reducing until it reaches 0. So it has to be like this. So what is this value? This is u and this is 0, right? At a particular time t. So you can write v is equal to 0 is that. It stops here, it will not continue. It will never continue because v0 means the vehicle stops. That's all. Okay, next graph I'm supposed to consider is the S versus T. Okay, so this is the displacement S versus the time T. Now you see, as the time progresses, the distance covered keeps on reducing, right? So initially you will start with 0 and, right, it is ut minus half at square. From ut you keep on subtracting half at square, because of which it will not increase, it's at the rate of change is decreasing. It's, right, keeps on decreasing here. Okay, so you know that ds by dt, right? What is ds by dt? Velocity has to be 0 at some point, right? So slope becomes constant, right? So I'll mark a point P here. You can see that I'll write a point below this. At P, calculate the ds by dt. What is ds by dt? Rate of change of the curve, sorry, ds by dt, this is t, equal to 0. That is the velocity. You see velocity becomes 0 here, right? So that's indicated by this. So as the time progresses, velocity keeps on decreasing, the slope of the curve keeps on reducing, and at the end it becomes 0. So that point P denotes the time at which the vehicle stopped. Okay, right? So uniformly accelerated and uniformly retarded or decelerated motions have been considered with the corresponding equations and the corresponding graphs, and it's easier to analyze the motion through graphs rather than solving the problems.